It is lecture number 3. Here we will talk about basic ingredient or basic concept of a probability measure or probability. So we will discuss in detail coming to outline of this lecture. First we would like to discuss about random experiment outcome and sample space in detail. That means once you are having a random experiment, you have to look for outcomes with respect to each trial of the experiment. You will get a result. That result generally we are calling it outcome, and we will try to see further inside the outcome how outcome is formed, how it is we are getting a result, how we are getting a outcome. Once we are having a collection of all possible outcome, that we term as a sample space. Once we are having idea of sample space, then I will take various example on sample space, how to come up with sample space for a specific random experiment. And afterward we will talk about events. So that means some possible uh, outcome which are of our interest. That means uh, we are willing to do something with some possible outcome. It is not like that always we have to proceed with all possible outcome. Some possible outcome would be of interest. So when we proceed with some possible outcome, that one is termed as an event. So various event would be there. Then we will talk about quantification of that randomness in that event, that term as a probability. We will do that through some probability measure. So one probability measure will come, and generally probability measure here we will define through empirical approach. Apart from that, we will put some axioms that will come from Kolmogorov approach, and it so that the definition becomes more concrete and it won't fail anywhere. So that is the part of this lecture. So coming to that first segment of this lecture, that random experiment outcomes and sample space. In detail, we will discuss all these concepts. Okay. So here, what is random experiment? In previous class, I had already described that it is an experiment whose outcome can't be predicted before the experiment is performed. That means if you toss a coin, you can't say prior to that result that what would come. You can't predict what outcome will come when you are going to perform an experiment in the random experiment. Simply it is not predictable to say. You can just guess that what would become. You can say that it just there would be one kind of it is not that it is not impossible to predict what exactly will come with certainty. It is not possible. So that's why that kind of experiment is termed as random experiment. Once we are having a random experiment, then we have to look for outcome. Each trial of the experiment leads to a result, that we are saying that a outcome. Okay, but if you try to look inside the outcome, then a typical random experiment, it involves several randomly determined quantities, and every possible combination of those quantities leads toward an outcome. So sometimes what will happen, that a random experiment might be very simple, and sometimes a random experiment might be very complex. So why? Because of various randomly determined quantity, involvement of various randomly determined quantities. So if you are taking a very simple kind of random experiment, like tossing a coin, then that happens to be a very simple kind of thing. Easily we will get outcome. But if you take very complicated kind of random experiment like Monte Hall problem, that time if someone is saying that what is the outcome of that Monte Hall problem, that when you go through experiment of that Monte Hall problem, then what would be the outcome? Then that outcome is not simple. You have to be very much focused in order to further see the sub gradient, which is just uh, constructing the outcome. So that's way in simple cases directly we are getting outcome, there is no issue. But if there is a random process, that random experiment that happens to be very, very complex, then definitely random experiment having various randomly determined quantity, and that leads toward construction of outcome. So that comes, even in that case, in complex random experiment, outcome becomes further what you can do a refinement within the outcome itself. Okay, that we will see it in detail. So uh, though the first ingredient of any probabilistic model is what, that we have to specify all the possible outcome of a random experiment. We have to just anyhow, ultimately once you perform, once you committed with the one trial of an experiment, you have to list out all the possible outcome. just specify what are the possible outcomes, whether the random experiment is very simple or complex. You have to come up with outcomes. Outcome is the ultimate starting phase for quantification of randomness. So that's where anyhow. And further, if as I mentioned that if the problem is complex, then definitely you have to look further inside into outcome itself, how it is coming, how the outcome is, what it is we are getting outcome from that experiment. It is very much essential. And as I had already mentioned that the collection of all possible outcome we term it as a sample of space. Sample of space. So it is second ingredient. So as I told that we are having a random experiment. First we try to look for outcome. What is the so outcome with respect to each trial we are getting a outcome. And if system is complex, then definitely uh, further some sub ingredient would be there, that also we have to look. So first starting uh, ingredient is outcome in way, in that way. Second one, that we have to list out all the possible uh, outcome, and that will form sample space. So two ingredient of this protein measure we have already, sample space. So in this segment, we will just focus on only two things. One is once we are having a random experiment, we'll focus on outcome and sample space. Okay. So suppose you flip a coin, then you know that either head will come as a that we represent it by H, or tail will come that we represent it by tail. Okay. And just you don't know which of these outcome will occurs in the given experiment in prior. You don't know in prior. Okay. So in this case, simply we can say that what is the sample space, and that will first, what are the possible outcome. So there are two possible outcome: either you will get head, or you will get tail. These are the possible outcome when you perform a but flipping of coin. So and hence you are getting sample. This one is the collection of all possible outcome, that we are calling it sample space of this experiment. So here it was very easy to identify what is outcome. Very easy to identify. Okay. With respect to, if you perform a how you can identify outcome, just flip a coin and try to see what you got. If you got head, then simply you will put out that outcome was head. If you flip a coin and you what you in second time, what you get tail, then you will point out tail. Again you flip the coin, what you get tail or head. So there are only two possibility of getting outcome, head or directly you are getting only two kind of outcome, head or tail. So those are forming a sample space. So both ingredient are over here. So that's why it is a very simple kind of experiment. Now let us complicate the uh, experiment. So what we do here, we are coming with a Monte Hall problem kind of things as a random experiment. So Monte Hall problem is the random experiment here we are performing. Okay. And we will see that how to design outcome here first. So that how to get first uh, ingredient, that outcome. So problem is coming like this way. Suppose you are in a game show and you are given the choice of three doors. Okay. Behind one door there is a car, behind other two doors there are courts. Okay. So that this one is already informed to you. Okay. Behind one door there is a car, behind other two doors there are goats. You don't know behind which one there is a car, or behind which one there is a goat. You don't know that. Only information is that you know that behind one door there would be car that you can treat as a gift, and behind other door those are goat. So simply you will look for winning the car that as a prize. So what are the further, what are further information? Moses, just switch off your microphone. Okay. So next level of information is coming to here in this random experiment. Definitely you will call it whether this experiment is a random experiment or not. Yeah, it is a random experiment. In prior, we can't predict So in flyer, we can't predict that car would be behind which door. So definitely it is random in nature. Okay. So what you will do? You will pick a door. Suppose it is door number one, and the what is happening? The host who knows that what is behind the doors. Host is already aware of that what is behind the door. So if you are picking a door, suppose say it one, then host will what do? He will open another door, and which is having a goat, and and after that he will say to you, do you want to pick door number two? Door number two. He will just suggest, would you like to pick door number two? Then you have to just conclude that is it your advantage to switch your choice, or you will stick with, because you don't have idea behind which door there is a car. You don't have what is the, that means one kind of sense that you have to find the probability of winning. Your winning, so you have to calculate the probability of your winning. So how you can tackle it? So anyone can comment over that, what would be the outcome here in this experiment, a random experiment? Anyone? Like just but is it no, I discuss about what is the outcome here in this experiment. I haven't discussed Bayes theorem here. It is not an application of Bayes theorem. It is just an application of a very simple probability, elementary probability, very simple kind of probability. I am not asking right now solution of this problem. I am just asking to find, assign the first level of ingredient that happens to be outcome. Find the outcome. What is the outcome here? Later we will see that simple space. Be systematic in order to solve any problem in probability. So first level of problem is here. What is the outcome in this problem? You perform an experiment once and try to find out what would be the possible outcome. So find the possible outcome. Anyone would like to suggest? Any idea? You can say I don't know, or you can say I know or don't. Very fair answer. It is not a and very a smart kind of answer. It would be if you rightly pointed out that I don't know. If you know, then very good as well. Anyone? First question is that how you can just identify what is the outcome. I'm talking about identification of outcome. If you are able to identify the outcome, then you will be able to solve this problem. And if you are unable to identify the outcome, then definitely problem will be very, it would be very it would be very difficult to solve if you don't understand how to come up with outcome. Any idea? How? Be systematic in mathematics. Yeah, that means you are in affirmative regarding that advantage of switching the choice. You are trying to give final answer. I am not asking for final answer. My question is right now, I am taking this problem as a random experiment, and my first question is that find the ingredients. So first ingredient happens to be outcome. Then once we are having an idea of outcome, then we will try to find out all possible outcome, and that will give our sample space. Next question would be what is the sample space in this experiment? Because you know that in your plus two you might have gone through probability. Always in any probabilistic modeling, always you come up with outcome, and then you are finding sample space. So that one is very much essential to find out all those things. If you are unable to see those things, how you can solve this problem? So this one is Kolmogorov approach, what I told, that very systematic approach. Later I will provide a systematic algorithm of probabilistic modeling. How there would be various steps. First step have to collect all the outcomes. Second step have to collect have to come up with sample aspect. In third step you have to come up with the event of interest, and fourth step you have to quantify the probability of that event. So there would be in probabilistic modeling always happens to be four step. In the four step, you come up with quantification of probability, and for the step, we come up with some probability measure. These are mm, okay, okay, yeah, okay, nice. Uh, you told that matlab, definitely like this way. Uh, at first, you are having three options of selecting the door. So it's any of three you can select with priority 1 by 3. Equally likely situation is there. Okay. Either you select door A, and give name to door. So call first door A, second door B, and third door C. So you can select each of any these two three door with priority 1 by 3. This one is the first level of information. Okay. What is the second level of information you are having? Okay. Uh, Simply let me highlight in a very systematic way. Nice, you are trying very nice in a very nice way, but not up to the what we call it. What I am asking, you have to be very much systematic in quantification of this problem. So here we have to list off all these label of information. What are the label of information? So first label of information is saying that car might be car is behind one of the three door. Okay, so that car you are treating as a price. So first label of information it say that that the do there is a do which is hiding the car, concealing the car. That one is the first level of information. So it is directly coming from here. So that will give this information now. Now come to second level of information. What is the second level of information? It is providing that the person that is selecting a do, that would be second level. Once you are having this idea, now second level of information that you are picking a do, that would be second level of information. So when you are coming, suppose you are uh, selecting a, then you will have second level of information, that either you can select do a, do you have already come up with that there are three doors, and any of these door will have uh, car price with priority 1 by 3. So this one is the first level. Second level of information, you are selecting uh, okay, among these you are selecting any one door. So this one is the what the player what initially choosing the door. Okay, so this one is the second level of information. There is a third level of information, that one is provided by that host. So third level information, that one is coming that the door that the host opens to reveal a God. So here you can see it. The host open the door to reveal that it is having a God. So it is a third level of information. So simply these are the given information, very important kind of information in order to solve this problem. But these are not outcome. These are not outcome. These are just sub ingredient. You can say that these are quantities given to you from the problem. Now by mixing these quantity, by taking various combination of this quantity. So this one is coming in first layer, this one is coming in second layer, this one is coming in third layer, this one is the third layer of information, you can say that. So all these will form a complete tree, and the last output of the tree, that leaf, final leaf, that would be our outcome that we have to see. So we are seeing the outcome, how we identify the outcome. So we identify like this way. Consider the one case we are taking. There would be several cases. So consider, through combinatory you will come to know how many possible cases would be there. Consider the doors are a b c. We are not counting door 1 2 3, we are taking as a abc. Okay. One we are calling it a, two we are calling it b, and three we are calling it c. As now, as the first layer of information, what we are having, uh, first layer of information, or first layer of the tree, that we are having, that the door which is concealing the price. This we are just taking as a first layer of door. Okay. So that we are having this, from the first information, that which door is concealing the price, through that we come up with this layer. Okay. This we are, you can term as a car location, behind which door there is a car. So with one probability 1 by 3, it would be behind A. With probability 1 by 3, it would be behind B. With probability 1 by 3, it would be behind C, because equally likely situation is there. Later I will talk about what is equally likely situation. Later I will talk in, during the probability measure process. Okay. So this one is the first layer of information, through car location, which door is concealing the car. Next, we try to look into, so for each feasible location of the price, now the player could initially choose any one of the three door as the second layer of information. After, once you are having first layer of information, you are looking for second layer of information. So with respect to that, uh, you just like here you can choose, there would be three opportunity always for you. This is the second layer, this is the second layer, this is the second layer. Layer might be clear to everyone. I am talking about layer. So this second layer is coming with respect to second sub ingredient. This one is coming with respect to first ingredient, and this one is coming with respect to player's choice. You can say that second layer information name, it is a player's choice. What player is opting for? Player's choice. Okay. Now there is a third level of information, that will define a third layer of the tree. So that one is that, when the host opens a door to reveal a goat. Okay, reveal a goat. Now my question would be here. Suppose this one is A. There would be again three possibility. You can opt for any of three door. Okay. Suppose you are opting A. Then what are the possibility for B? It would be. Or what are the possibility for host? If you are, suppose you are player, you are opting for this door, then what are the possibility of, hmm, 2 by 3 possibility? That means, host will either open B or C, because host know about, the what location of price, where car is there. Host know about that. So that's why for host, uh, either host will open the door B, or will open the door C. That's one. So this one is the third layer of information. Likewise, if you are opting for, see, as a player, you are opting for door B, then what host will do? What would be the third layer? Very nice. That person will go for only C, because that host has already, uh, uh, first layer information we are pursuing, has already seen A and B as well, because of your activity. So that's why C. So this way, if you talk about this path, this path, then if you just trace out how this path, what is the leaf of this path, final product of this path, if you try to see, so it will simply A, A, B, 1, it will give. That means you can term it as a a b. And similarly, if you talk about leaf of this one, what could be a a c a c. So this is the outcome. This is the outcome. I was asking find the outcome. This is the outcome. So we'll try to see. So here, just I am mentioning it further again. I will list out all those outcomes here. So if the price is behind door A, suppose price is behind door A, then the player, and suppose in the first layer we are assuming that just we have to identify out the outcome. So it is, suppose the price is behind door A and the player is picking door A, then host could open either B or C. Why? Only why we host will open B or C only? Any idea? We are just we are trying to identify the outcome. Yeah. Yes. Yeah. Host know everything. What is behind which door? So host know. That's way. mm, just for the sake of game, that player we, to make change your belief, to change your option or change your opinion. Host is not going to open the door what you have already opted. Host will open door other than you have already gone through supposition. Okay, that's why host will open B or C. See, with respect to that, you will get outcome. If your host is opening the door B, then corresponding outcome is AAB. If host is opening door C, then corresponding outcome is AAC. So this is the final outcome of the Monte Hall problem. One outcome. Now, next outcome, there is one more scenario. If the suppose price is the car or price is behind door A, then player is picking in the second layer information. Player is picking the door B. Then what will happen? Host is already aware of door A and door B, that has gone through those layer wise information. So definitely host will have only one option C. So host will open C. That means you are getting the outcome A B C. Likewise, in the process, you will get all the possible outcome. This one is the first layer of information. That one is giving uh, this tree, this part of the first layer of uh, this tree. This one is definitely a tree. Now after that we are using second layer of information, that is what is the initial guess of that first guess of player. So that we are seeing, this is the, you can see that each end of each first layer end, what each node is having three options. Here is player will have three options. All will be again equally likely. Equally likely. All these would be equally likely. Now this one is the host reveal. Host is going to reveal third level of information. Due to that, we are getting third layer. So you can say that suppose you are suppose car is behind door A, then and player is opting for A, and in that case host will open either door B or door C, and hence we are having two possibility of outcome. This one is AAB, this one is AAC. Likewise, if suppose car is behind door A and host that player is opting B in second level information, opting B, and in that case the host will reveal C. Host will open door C. So you will have outcome A, B, C. Name of that outcome would be after the that Monte Hall problem. Name of outcome, that experiment. It will, this outcome is possible. Now suppose car is behind door A and you are opting for C. In that case also, what will happen? Host will open. Will have only one possibility, that with protive one, host will open door B. So with respect to that, you are getting outcome A, C, B. Likewise, just construct all the leaf BAC. This would be This would be BBA, BBC, BCA. Okay, all these you can find out all this. So in together, if I'm asking you, come up to see what is the outcome. So these are the outcome. If you want to solve this problem in a very systematic way in Kolmogorov approach, you have to come up with outcome. What is the final outcome of one experiment? So collect all the possible outcomes. So these are the possible outcome and bring it together, and you will get a sampler space of this problem. And this is the sampler space. You got it. This is the sample of a space of Monte Hall problem. Now, next question would be there. You can find one event would be given to you, and you have to find the respective probability. But here I am covering here right now only two ingredient outcome and what we call it. Second one is sample space. So you are having everything. You come up with outcomes. You come up with sample space. So both answer is already given to you. It might be clear to you. Next, we are going to discuss about few more example from the what process of finding sample space. This would be very simple. Okay. Any question? I think that might be clear to everyone. Later we will discuss that. Right now, just we have to be systematic. Everything. If I solve it here, then it would be very much what we call it complex. So I will solve that later in later part. I haven't discussed event till now. Okay, I have to discuss event, then I will discuss. So when I will discuss probabilistic modeling, I will take a problem and try to find all the ingredients, and you will see the probability. So I'm just right now relying with uh, ingredients. So first I discuss about how to find outcome. So that I have already given. Next, also I discuss about how to find sample space, that I discuss. So we have to find outcome. Next, we have to find sample space. Third one is uh, event, and fourth one would be probability measure. After that, we will solve problem through probabilistic model. So it is very much essential to know what approach you are going through. So that approach, it would be based on equilikely situation. You will see that what would be the algorithm would be based on equilikely situation. After covering these four, we'll talk about all the process of calculating quantifying probability. So just we have to discuss two more ingredient to make things more important. Okay, so here again same problem. In last class I had discussed that if you consider a random experiment of throwing two dice. Okay, two dice, then the outcome, one outcome simply uh, it would be here like this way. Again, if you try to reflect that again in a tree wise, then there would be a tree with two layers. So in first layer, how many options would be there? First layer, you can say that it is red dice, or whichever you want to take. So how many leaf would be in the first layer? Six. This is the first layer. Okay. Likewise, again in the second layer, how many leaf you will have? Six. So you can observe that how you have to come up with outcome. So it is very much essential to identify outcome. So you can name one, two, three, four, five, six. Likewise, here you can name further. And these layer are coming with respect to second dice. So likewise also you can. So there are two layer, and final outcome would be here. Final, that would be outcome. So how to design outcome, you need to understand in a very interesting way. You have to visualize all those outcome process, how you come up with outcomes. This one is the first layer of information, this one is the second. First layer of information, how you are getting it by throwing first dice. What would be first dice? Might be red, or might be blue. Depends upon your convenient what you want to proceed with. And then second level of information, it would be provided by that tossing of second dice, rolling of second dice. So that's why we are getting two layer, and finally this leaf will give our outcome. And hence, what would be simpler space? Simpler space, it would be order pair. Suppose I is coming with respect, here you can give name I for this, any one of six, okay, and J for second layer, anyone. So Ij. So in total, how many element you will get? You will get 36 element that we had already discussed. So we got it through layer wise. So how you are getting outcome, that as a first ingredient, and second ingredient is sample space. List out all the possible outcome and you will get the sample space. Okay. Next, we are taking another example, that again waiting time approach, that consider we are having a random experiment there. You have to wait a bus that will arrive at a random time in the future, in order to, if you want to go somewhere else from one bus stop. In this case, as I mentioned that in last class, that what would be random variable? It would be waiting time, and waiting time would be always greater than equal to 0. And you know meaning of t equal to 0, then instantly once you arrive at the bus stop, you got the bus. That is meaning of t equal to 0. And what is meaning of t equal to 1.5 hour? Meaning that once you arrive at bus stop after 1.5 hour, you got your bus. Okay, so that is the meaning of. Okay, in that process, the sample space here simply it would be a semi closed interval 0 to infinity. Okay, so this is the sample space. Both ingredient we got it. What is the outcome? Okay, arrival. What is the outcome? Okay, t equal to 0. So t equal to 0, what does it mean? T equal to 1.5, or what does it mean? So each value of t is giving a outcome. Each value of t is giving a outcome, so that it easily we are getting meaning of outcome. So this experiment is very simple experiment. It doesn't need more than one layer of information. Just a very simple kind of way. This second experiment is a very simple kind of experiment. First one was a little bit complicated. I think this one is third example. This one is second, and first we had already discussed about Monte Carlo. So here again you can see that this experiment is a very simple kind of experiment. Easily we can identify outcome. The t equal to 0, t equal to 1.5, these are the outcome, and various separate individual value of t you will take, that will reflect an outcome. And in totality, if you specify all the outcome, then you will get your sample space. Now, coming further, few more example, like this one is also very interesting. It will be in random process. You will see it like suppose a bee is buzzing around, and we track its flight trajectory for 5 seconds, just for 5 seconds. 5 seconds means simply 0 to 5 seconds. We observe for 0 to 5 seconds. Okay, so we have to find what possible outcome are there in such experiment. So we have to identify what is the outcome. Next, we have to identify what would be the sample space. Anyone who would like to say that what would be the outcome if a bee is buzzing around you? That this kind of experiment might be very much common to everyone. Everyone might have encountered that kind of situation. Mosquito or bee or something like that. Or you can if you haven't experienced or have if don't have any experience of bee, just replace that with mosquito. So tell me what would be outcome here? That means the path bee is taking in the process of buzzing around you, in the process of moving around you. Okay, yeah, nice try. So here, let's focus on this trajectory. What does it talk about? Okay, just one question. Try to answer. What is name of this course? One question, simple question. What is name of this course? Yeah. So intentionally question would be from that background probability. If you are putting angle, can you anyone can you say that can you measure the angle of flight of a bee or flight of a trajectory? Flight means just motion; it is moving from somewhere. Anyone can say that is it when you measure that means you say that it is a deterministic in nature. Flight how flight move flight of the bee? What is the nature of flight of bee? Or what is the nature of flight of mosquito? Can you predict in advance? What it is totally random in nature. Totally random in nature. You don't know how it would be very zigzag kind of. If you try to observe path of the bee, any bee, it just take any starting point and just you observe up to 5 minutes. So it would be very zigzag kind of this kind of situation. So what is the name of this one? If I plotted, anyone would like to say that uh, here this one is this horizontal axis is t axis. I'm trying to develop the concept so that you can model a probabilistic phenomena. You go up to 5 seconds. We are measuring t unit of t is 5, and this one is 0. And y axis is talking about path, the value of that value of the this okay value of this person. So what does it? What is it? Is just a trajectory of one b. There may be another trajectory. That trajectory may start from somewhere like this way, like this way. There are various trajectory, collection of trajectory. You will see. So, what is anyone would like to comment? What does it mean? What is this one? What is this? It is a continuous function of time. Simply you reflect it that is it is a continuous function of so outcome generally if you will know onward you will see that outcome generally we denote it by omega and it is just omega is what y-axis is omega and omega it is a function of time and it is a continuous function. Say one outcome you talk about it is a path, it is a trajectory, path trajectory. And when you talk about path, it always happens to be a graph of function or some kind of what is that? Here, always be taking a continuous path. It is not like that. There would be some kind of discontinuous approach. That path of B would be always continuous in nature. So it is simply a continuous function. So outcome you have to identify. This is the outcome. But you remember that the path would be very zigzag in nature, very rough. It would be not ideally a smooth. Why? Why roughness is coming? Anyone would like to point out why this roughness is coming? You know meaning of roughness. That kink or roughness. That means roughness, not a smooth. That means not a smooth means not differentiable. At few point, this function would be not differentiable. That means rough. This one is a rough path or non a smooth path. That non there is some differentiability issue at certain point. So this would be one outcome. That means uh, flight trajectory of one B, one mosquito or bee. So why and this zigzag nature is coming? Anyone would like to point out? At very first class, I had discussed one thing that regarding that gaseous molecule or fluid molecule. Yes, any? Yeah, definitely it is a continuous. My question is different. My question is why this roughness is there, zigzag nature is there. I didn't ask discontinuity about discontinuity or continuity. I asked why zigzag nature is there or why roughness. Zigzag nature, that simply we say that it is there is a roughness where it is not a smooth means it is a rough path. You see that zigzag here, there is a king. Definitely this path is not differentiable at this point. It is not a smooth path. Yeah, very nice, very nice. Same motion is here totally random. Motion of the bee or motion of mosquito is totally random. And why, how randomness is originated? That means if you see in a, micro level, microscopic level, then what is happening that when one mosquito is just taking a flight, definitely in the path of that flight, another mosquito will come, and due to that collision and or about to be collide, one mosquito that will be about to be collide, so that's where there would be a sudden change in the direction of motion. There would be a sudden change or random change, so random activity is there. So due to that random movement of the bee, we are getting this zigzag path. Random movement, randomness, due to randomness, you are getting like fluid molecules having random collision, and due to that collision, molecule is changing the path. You might have already seen that simulated version. I had already explained that in very first class. So due to that say, so that's why due to randomness we are getting this kind of situation. This one is one outcome. Here outcome is a path. Remember that outcome of this experiment is a path. Okay, as we have not yet discovered the secret of teleportation, their flight path can't have any jump. That means if one bee is just taking a path and some another bee is coming in between, then it is not like that the path will jump over that. Just that bee will change the path, change the direction in the process of path change. Bee will not change the path, change bee, that bee will change the direction in order to trace out a new path or his or its path. Okay, so that's way. So hence, what will happen? What would be sample space? Sample space would be collection of all continuous function defined from 0 to 5 second in suppose it is in 3D. So in R3. So this is the sample space. One outcome you have already seen that it is the path as a continuous function with time interval 0 to 5 second, and definitely that B is buzzing in a space. That what is the data space? Generally it happens to be 3D space, so that's why codomain would be R3. So this is the sample space of this path. Both this first level we are having outcome, this one is the outcome. First level ingredient we are having outcome, second we are having sample space. So understand how to come up with this ingredient. This understanding is very much essential in this course in order to quantify probability. I am always saying. Now we are coming to discuss about third ingredient that happens to be event. So we'll discuss a detail about this, how to define events, and how how to list out possible events or event of interest. Generally, here event means event of your interest. What problem is? From problem, it would definitely it would be there would be a signal which will say that what kind of outcome you are going to list out in the event. So event, since once we have defined all possible outcome of an random experiment, we should discuss what type of question we can ask about that such outcomes. That will define our interest. It will based on interest, and that will lead to our event. So this will lead us to the notion of events. Informally, if you talk about what is event, event is a statement for which we can determine whether it is true or false after the experiment has been performed. It is simply one kind of mathematical statement. We say that. So suppose you are taking same experiment of performing. two dice, roll of two dice. So consider the experiment of throwing two dice, and we did not outcome by order pair ij. I is coming from first roll, j is coming from second roll. So that's the order pair. So this is the outcome. Okay, outcome. So consider the event of interest that we put it here. The sum of numbers on the dice, it would be 7. That means we are performing rolling of two dice. So that sum would be 7. Sum would be 7. Once you fix that statement, it is a mathematical statement. So once you fix a statement, then it will list out uh, those outcome which satisfy this statement. So we will only consider only those outcome which are satisfying this statement. Which are not satisfying this statement, which will not come in that event. So simply that's why I had told that this one is saying that it is not talking about all possible outcome, it is talking about some possible outcome, and hence we are getting an event. If you change the statement, your event will be changed. If someone is saying that some would be 8, some would be 9, the based on that you will get various uh, outcome. Some possible outcome we are seeing. So here simply I would like to point out here directly, I won't take much time. So what are those, so among those 36 outcome possible outcome, what are those outcome which will have some one? So if you take if you go systematic well ordering property, you can say that if you take one from if you see take one from first dice, six from second dice, and you sum up, then sum definitely is 7. Likewise 2 from first dice, 5 from second dice, and you sum up, it will be 7. If you 3 from first dice, 4 from second dice, then roll of second dice, then sum is again 7. So these are the possible outcome which satisfy this statement. So this will form an event. So event is just some possible outcome. Some possible outcome, that one is defined by this quantity. So we got event. So definitely by default event would be a subset of sample space, that we know, everyone know that from set theory we say that. So this is the approach, that we have to come up with one mathematical statement, and we have to look what kind of outcome is going to satisfy that mathematical statement, and hence we will get an event. So it is very much essential to identify the events of interest. I will take another things about the event. So we cannot predict in advance whether this event will occur, but what will happen? We can determine whether it has occurred once the outcome of the experiment is known to you. Okay, we cannot predict in advance whether this experiment will occur, but we can determine whether it has occurred once we will have idea of we idea of outcome of the experiment, that we might have seen. Then we can say. So again, we talk about waiting time game, that waiting time example. So suppose consider the random experiment of waiting for a bus that will arrive at random in the future. Okay, where you are waiting near a bus stop, a nearby bus stop, you can observe that, you can consider. Now we have to come up with one mathematical statement that will signify our that will lead to our definition of event. So consider the statement like this one, like the bus comes within first hour. So it will define in a statement. So we have to look for only those buses uh, which will come in first hour. That means waiting time is what? First hour. T first hour. What does it mean? By default, T will if you are arriving in a bus stop and at instant you are getting a bus, very non T equal to 0, outcome will be also there, and T equal to 1, outcome 1 hour would be also there, and between these two outcomes 0 to 1, it is a continuous outcome is coming in continuous fashion. From 0 to 1, all those also falls in this category. It will satisfy this statement. So that's way, if you talk about outcome of this experiment which is satisfying this statement, it would be what? It would be just unit interval 0 to 1. Remember that here unit is hour. Unit interval, I am saying that unit interval, that in interval which is having length 1, we are saying that interval unit interval. But another term I use, unit. Unit happens to every physical quantity is having, when you measure it, that one is having any unit. If you are measuring mass will have unit kg. If you are measuring time will have unit second or hour or minute, depends upon your convenience what you want to proceed with. Okay, so simply event would be that what, the waiting time that between, that falls between 0 to 1, is satisfying this mathematical statement, and that will define an event. So it is definitely, this event is a subset of sample space of this random experiment waiting time random, that happens to be sample space 0 to infinity. So now next part is that we will try to find out probability measure. And uh, that someone asked that what would be event of Monte Hall problem, that I will discuss that during modeling, probabilistic modeling approach. That problem happens to be complicated little bit, that's why I'm just delaying that. So I will discuss in next part. Okay, so first let me recall about what is the probabilistic measure, how we can, that means we are coming with some kind of numeric approach to quantify probability or randomness. So how we define probability measure? So after specifying this sample space of all possible outcome, sample space omega as a all possible outcome, then after that we are looking for events, and that one is satisfying some mathematical statement, and hence simply it is saying that it contains some possible outcome, or we can reason out few things. Now we see how does a experiment work. You pick one outcome, we will give name to outcome here. Till now we haven't given notation for outcome. Only sample space we are denoting it by uh, omega, capital omega. And we know that from the set theory, if you are defining a set, then member of set generally we denote it by a small letter a, such that a small a belongs to the given set A. Set generally we denote by capital letters. That's why here outcome happens to be a member of sample space. That means an element of sample space we denote it by a small omega. This one is the small omega. This one is the capital omega. So if you pick one outcome omega from the set of all possible outcome, that is just you are taking it from sample space. Once this outcome is revealed to us, we can check for any event whether or not that event occurs in this process of realization of the experiment. By how we will check whether A occurs or not. If what outcome we had taken, that outcome falls in this event A, that means uh, omega, this outcome omega is satisfying the statement. Some kind of a statement might be involved with respect to this event A. If this omega is satisfying this event, then simply we say that this outcome is in this event. If this omega is not satisfying this event, a statement related to this event, then simply we will say that omega is not in this event A. That is the checking process of event. Okay, so unfortunately, we have no way of predicting which outcome you pick before conducting the experiment. Before conducting the experiment, you can't predict which outcome you have to proceed with. Okay, therefore, also we also what is happen. Also, do not know in advance whether or not some event will occur. Also, we don't have any idea of occurrence of an event prior to that experiment. So, what we have to do? So to model an experiment, we will specify for each event A our degree of confidence. That degree of confidence we will call it probability measure. Whether, so what does it talk about? It is the degree of confidence. It is about whether this event will occur or not. So occur with what degree of confidence? So that degree of confidence, we will measure it through a number, or we will assign a number. That number we will denote it by P of A, and this number will fall between 0 to 1, which must obey some rule. So we come up with this. We are having an event A. It is satisfying some mathematical statement. It is defined by some mathematical statement. After that, what we do, we come up with a number or degree of freedom. We denote it by denote a P of A. Don't call it right now probability of A. So this number is taken in such a way it falls between 0 to 1. And now after that we will put some axioms. Okay, so which uh, must obey some rule or axioms that encode our common sense about how random experiment work. And hence if you are putting encoding all these rules or axioms, then we will call this degree of freedom, it is actually a probability to event A. So here you can see that this process is totally reverse. We are not defining probability of A directly first. We are just assigning event in assignment number or degree of freedom. We don't know right now how to come up with the explicit value of formula of this one. Later we will see that through some axioms we will come to know explicit representation of P of A. Right now this one is completely abstract in nature. Okay, so suppose someone is saying that this degree of freedom for an event is equal to 1. What does it say? Then we are very simply say that we are very much certain that event will occurs. In this case, A will happens every time we perform the experiment. Like two-headed coin. If you take a two-headed coin, what is the probability of getting head? It would be always equal to 1. Probability of getting head would be always equal to 1. So that situation is coming. That means that one is a very certain kind of there is no randomness, and that one is a very certain kind of what we call it experiment. If suppose P equal to 0, that means we are certain that A will not occur. We are certain that A will not occur. In this case, A never happens in any experiment. Like if you are taking two-headed coin, and then definitely there is no guarantee that you will get tail. Anyone would recall who had two-headed coin in any of the movie? Anyone? Are you listening me? Yeah, you're talking about movie, that which person had that? Be a specific. It is not like just naming the movie. That Jay had that coin. No? That okay. Okay, that what does it mean? There was no any option that Biru might have won any time. It was certain. It was certain that in every toss, one candidate definitely was a loser, and another candidate was winner. So those are certain. No, certain experiment. There was no randomness. Now, suppose you are having an event whose probability is zero point 0.7. Then what does it say? Then it says that the event will occur in some realization of the experiment, not in others. That means if we run the experiment, we are 70% confident that the event will happen. 30%, in 30% we are not sure, but in 70% we are sure. So here definitely degree of confidence is now decreased from 1 to zero point 0.7. It has been decreased. So that's where degree of confidence, it is very essential kind of quantification. We are trying to quantify probability. We are trying to go through quantification. So till now I haven't discussed how to calculate this degree of confidence. I haven't discussed. I remember that. So stay with me. Definitely, we'll come to know how to quantify that, and that would be really interesting. So, intuitively, this specify the likelihood of an outcome, of any outcome, or of any set of possible. Here, remember that. Focus on all the words involved in the statement. Okay. So here Intuitively, these specify the likelihood of any outcome or any set of possible outcomes. I am not mentioning all possible outcomes, any set of possible outcomes, or some simply you can replace that one some outcome, some possible outcome. Don't leave possible outcome. If you leave the possible outcome, meaning would be died. Some possible outcome. You have to see the possibility. Whenever there is a probability, you always look for possibility, some possible outcome. That is the event. What we call it. So, a probability measure, it is an assignment of a number P of A to every event A such that it satisfies the following rules. What are those rules? First rule is say that the assignment number or confidence degree of confidence, it lies between 0 to 1. 0 is talking about non happening, or we talk about impossible kind of things, and 1 is talking about certainty, that means always possible. So P always lies between 0 to 1. If it is in between 0 to 1, then there is an uncertainty. So simply we can say that probability, it is a measure of confidence, and it would be always non-negative, that means greater than equal to 0. Here you can, from left hand side, you can see that degree of confidence would be always greater than equal to 0. That means non-negative. Second, it would be if it is equal to 1, we are certain that something will happen. That we say second condition. This one is normalizing condition. A probability of that if you trying to find degree of confidence for sample space, the sample space is what it is talking about, all possible outcome. That if you perform an experiment, definitely that outcome will fall in the sample space, that you are very much sure that the outcome will falls in it will be contained in the sample space. So that's why probability of sample space always happens to be 1. Happening of sample space is always certain. Why? Because you are just specifying all the possible outcomes. So that's why at this property we are calling it normalizing property. This we are calling it normalizing property. Now, third, if you take any two events A and B, you are taking such a way you don't see any common outcome between these two, like getting a head or getting a tail. Do you see any common outcome between head and tail? Anyone? No. So that situation we are talking. So there is no common outcome between those two. Okay. So then, what would be the probability of A intersection B? It is just summation of the individual probability. If there is no common outcome between A and B, then how we can calculate probability of A union B? Or simply we can say that what is a total? This one is the total probability of A and B. So it would be just by summing the individual probability, then we will get total probability. This law we are calling it probability of mutual exclusive events. It will add up. So here A and B both are mutually exclusive. So remember here, what I would like to translate it further. Here you can talk this third one, mutually exclusive. Mutually exclusiveness. Exclusiveness. Now, anyone may point out what is the another name of second property? Another name of this property? Anyone would like to recall? Because all you have gone through that probability class. So just try to recall. I'm just rephrasing few things right now. Odd probability of any, like in term of mutually exclusive, we discuss third property. Another name we can say that mutually exclusiveness. What is the name of second property, that normalization property? Have you heard? It would come in the what Kolmogorov approach. So that's why I'm talking about this. You know all these, but unable to recall right now. So this property normalization property, again you can say that it is talking about exhaustiness, total exhaustiness or exhaustiness. Total would be hidden here, exhausting, exhaustiness. That means it includes all the possible outcome. So that is the meaning of total exhaustiness. Total is hidden here, but you can mention here total. Second property you can call it, a name of this one is total exhaustiness. So more generally, you can generalize this one, third one. Suppose you are having n number of or a countable number of mutually exclusive events. This one is talking about mutually exclusive. If you take any two event and there is no outcome between any two pair of event, then simply those would be mutually exclusive. And if you are willing to find the probability of union of all these, then it is very simple to find the individual probability and sum it up. So again, this law is just a generalization of mutually exclusiveness. So again, you can say that this law is also mutually exclusiveness for with respect to more than two event. So all these are law. You don't have to prove all these. You have to just proceed with. That means you had a number P of A. It is satisfying these three properties. Till now, just we come up with one degree of confidence which is satisfying all these three properties. And after that, we will see how to define P of A. So here we will go through different approach. That one approach we are calling it frequentist approach. We try to find probability of A through frequentist approach, and also we will use common sense. This frequentist approach itself is not sufficient to discuss about the probability measure. We have to come up with some common sense. So intuitively, probability study and it study and compute, or you can say that quantify randomness of an event. If you flip a coin many times, then the coin will come up heads roughly half the time. If suppose you are flipping a coin 10 times, 10 times your number of trial is 10, and first time suppose you are getting head, second time you are getting head, third time you are getting head, fourth time you are getting head, fifth time you are getting head, sixth time you are getting head, seventh time you are getting head, tenth, eighth time you are getting head, ninth time you are getting head, 10th time you are getting tail. I'm okay with this outcome. Is it possible to get such kind of outcome? If you are performing a coin 10 times, is it possible to get this kind of outcome? Is it possible or not? So, yeah, yeah. So if I ask, what is the probability of getting a hit from this 10 number of trial? What is the probability of getting? What would be? So event is that 9 head and 1 tail. So your answer is coming 9 by 10. But you are saying that always we had already discussed probability of getting head is 0.5. Mm, where is the issue? It is not equal to 1 bit. Where is the issue? Yeah, what? I could not listen you. Here, simply you can say that here that law of large number is coming here. That one is part of model 3. So if you are just having less number of trials, then from the less number of trial, you can't get the probability of head accurately. That one is matching to axiomatic definition of probability, axiomatic definition. Right now this one we got it through empirical approach. So we this one is the empirical approach. That's why empirical approach always fails in when your data is less number of trial. That one is data provided is less. When suppose data is more than enough sufficient, then you will say that when you will calculate this probability of head, that would be roughly equal to 0.5. when number of trial is 100, 200, 1000, something like that. When you increase the number of uh, trials, when you increase the number of trials automatically, so simply you can say that this probability is what we have calculated like this way. This probability of head we have calculated like this way. Number of times head is coming, that we are calling it, okay, number of success. Getting head we are calling number of success, and total number of trials, k by n. Okay, this probability we are defining it. So what kind of definition this one? This one is an empirical definition. This one is an empirical definition, and if you take n is suppose very large, and then in that case it will be definitely very near 2.5. That one is part of law of large number. We'll discuss in detail that in model 3, law of large number. Right now we definitely, so that's why I'm not till now I haven't, so due to all these compulsion I haven't given explicit form of this probability of a, this degree of confidence we haven't given explicit form. I am saying that it is just a number that lies between 0 to 1 and satisfying three set of properties. So that I have discussed about. Okay, so uh, so after that we will come up with few more uh, concepts, so that we will get explicit form of this p of a. So don't use right now directly this one, don't you will face problem. So thus we say that the probability that the coin will come up head is one half. More generally, that in large run of the uh, tossing. Okay, so more generally our common sense entity about probability is in term of frequency. Like generally we denote the probability, that p of a, in term of frequency, that means number of success divided by total number of trials. That means if we repeated a random experiment many times, the probability of an event is the fraction of the experiment in which the event occurs, k by n. Okay, as we have seen the heuristic, this one is heuristic. We are saying that empirical or heuristic definition in terms of fraction that can lead to ambiguous conclusion. Here, like one ambiguous, that p of head it is coming 9 by 10, and that one is totally wrong. Probability of head must be 0.5, but we are getting 9 by 10 through this 10 trial, and after observing this outcome. So this is why we do not define probability as frequency, like probability, like in this heuristic approach we are not defining probability directly. So due to that we are not defining. Okay, then how we will define? Instead we make an ambiguous unambiguous mathematical definition of the degree of confidence, that probability of a. How we define? To every element. So we encode common sense into mathematics by insisting that these number must satisfy some rule, that are precisely the properties that frequency should have. So apart from the frequency we have to come up with common sense. We have to encode common sense. So what are those things? So one, first, the fraction of experiment in which an event occurs must obviously by definition be a member between 0 to 1, be a number between 0 to 1. So what fraction we are getting? It must be between 0 to 1. This one is one assumption. Second, as omega is the set of all possible outcome, the fraction of experiment where outcome lies in is obviously 1. Same thing what I had discussed. Probability of sample space must be equal to 1, and probability of an event A you are taking must be lies between 0 to 1. And third one is that mutually exclusionist. Same thing I am saying. Again that same thing I am saying, that this is the these are the common sense. Very much. So in next class we will discuss about I think it is already around uh, 12, 10. So in next class we discuss in detail about how to come up with probability of explicit form of probability of A. So before that, just I will give one look over this. What is probabilistic model? So probabilistic modeling, it is a mathematical description of an uncertain situation in accordance with three ingredients, that happens to be sample space, that happens to be probability law, that happens to be probability measures. So till now we have discussed about first one is sample space, we have to discuss about probability measure. That means I haven't given explicit law, right? I just discussed that this must lies between uh, sorry 0 to 1, and first one is this through probability measure we discuss. First is P of A lies between 0 to 1. Second, P of omega must be equal to 1, and third one is mutually exclusive. So this. Then apart from that, there is a third one that we are calling it probability law. So here this probability law is coming through different what kind of law you want to introduce. So one is that equally likely situation. Anyone have you heard that equally likely situation? One law is equally likely, another law there is a uniform principle will come here. Have you anyone have you heard that equally likely situation? Anyone? What is meaning of that? Yeah, just you tried well, but you made a mistake. Probability of we won't say that probability of event. We will say that probability of each individual outcome would be same. Then we say that that random experiment is having equally likely situation. If probability of every outcome is same, equally likely means same, then we say that that experiment is satisfying equally likely law. So equally likely it is a law that we are putting. So when you are saying tossing a coin, if you toss a coin, and you put a law here, law will come here. Remember that a law here to sample space, you are already having probability measure, you come up with it is a number satisfying these three property. Now after that you come up with a law in the tossing a coin, you say that uh, outcomes are equally likely. Just you put a law in a statement, outcomes are equally likely. uh, I need to write in proper way. Outcomes you are putting here, here, here in the this experiment you are putting equally likely or put full statement, outcomes are equally likely. What does it mean? It will say that we are having, what are the outcome in tossing a coin? We are having head and tail, and so we are having simple space. So due to this equally likely situation, equally likely, what would be probability of head? It would be equal to probability of tail. Through this law, we come up with this equally likely situation have satisfy this one. Now, come to talk about probability measure. What does it satisfy? It satisfy a probability measure satisfy all these three property. That means this probability of head and probability of tail. There are only two outcome here. in the tossing of a coin. So both quantity would between 0 to 1, first law. Second law, what does it say? It is talking about probability of sample space. That means probability of head and tail in together, if you take, it is equal to 1. Third, there is a third property. If you talk about probability of head, take it like this union. Mutually exclusive. Head and tail are mutually exclusive. You can talk here. It would be equal to sum of probability of head plus probability of tail. Now, just simplify these three axioms. What you will get? Anyone? If you simplify three axioms, what you will get? Probability of head plus probability of tail, and also including this equally likely situation. This call equation 1, and these are coming as a law. So here simply probability of head and tail union, if you take a head and tail happens to be mutually exclusive. So simply what would be probability? This probability equal to 1. So simplify equation 1 and equation 2. What you are getting? Anyone respond? What you are getting? You are getting a numeric value of probability of head. That one is equal to 1 by 2. And similarly you are getting probability of tail. That one is also 1 by I. Here you are not committing any mistake. You are perfectly fine because you went through arithmetic Kolmogorov approach of calculating probability. So see the remember here you come up with this here. How you come up? You come up with a probability measure which is satisfying three probability. You come up with a probability law which is what equally likely. So using probability law and probability measure and rest of other ingredient, then you are coming with a numeric value of probability, and here you are not committing any mistake. So this is the approach. You have to understand what is the law, probability law. So here directly we are able to quantify the probability. So here you are not committing any mistake. There is no any mistake. So other things we will discuss in next class regarding attendance. Just put your roll number there in comment box.